Section 5.1 Areas and Distances. We are going to learn here how to use calculus to find the area under the curve. So back in elementary school, we learned how to find the area of a triangle or parallelogram, square, rectangle, trapezoid, rhombus, kite. So all that, they had their own formulas. The question that we have here to show us how powerful calculus is, how can we find the area under the curve like this? Let's say that's the function f, the x-axis, y-axis. Let's say I want to find the area from x equal a to x equals b under the curve. And this can be difficult to find using just rectangle or just because that shape is not like one of those standard shapes that we're familiar with. And that's where calculus kicks in. We are going to use calculus to find the area under the curve. For the meantime, in this section, we're going to do some estimation first, and then we'll show you the exact area under the curve. And then in the next section, we continue in the next section to come up with different tools, easier tools than going through a lot of tedious work to find the area under the curve. So for the meantime, I'm going to show you by starting with an example. I'm going to start with an example. Estimate. Ask this as a question. Estimate the area under the graph of the parabola y equals x squared from x equals 0 to x equals 1. So let's see how we start with such a thing. So let's start. First thing I'm gonna do here on the side is sketch the graph. So the parabola, let's say, goes up this way. Zero to 1. So what I'm gonna do, I'm going to split this into say 1 is here. I'm gonna break this into 4 intervals. So what I'm gonna do, this is 0 to 1. We need to find the area under the curve for that part. This shaded one. We're gonna find the area under the curve. So to do this, the first thing we're gonna start is I'm going to break this 0 to 1 into different we call them intervals or sub-intervals. So I'm gonna have 1, 2, 3, 4 intervals. So that's 1/4, 1/2, 3/4, and 1. Okay, and if you like to know how I get these numbers, we always take the highest minus the lowest divided by how many rectangles or intervals we need. We need 4, so it's 1/4. So every time you add 1/4, 1/4. And let's say someone started on the right side. Watch how I'm gonna do this. I'm gonna draw a horizontal line and then take this up all the way up. And then whatever intersect the curve, go another horizontal and up. Like that. And then whatever intersect, go horizontal. So now what I'm gonna do is I'm gonna find the area of those 4 rectangles and add them up. So that will give me an estimated area comparing to the area of the shaded region. So how do we find the area of the rectangles? It's not difficult to do so. So to find the area, the sum of the areas of all these rectangles, first thing, let A be the area we're exactly looking for, area of the shaded region. So the area that I'm gonna find, which is A, let me call it A again, is gonna be estimated with the sum of all the areas of the 4 rectangles. How do I find the areas of the 4 rectangles? So the area of the rectangle is length times width. So if I want to find the width of the first rectangle here, this highlighted one, the length is 1/4. So it's 1/4, the width is 1/4, and the height, what's the height of that rectangle? So to find the height of the rectangle is basically we look at this part from here to here. That's the height. How do I find that height? That's really the function evaluated at 1/4. So it's 1/4 squared because the function was x squared, plus the next rectangle 1/4, and then the height of that next rectangle is this one. So it's evaluated at 1/2 square, plus 1/4, then 3/4 square, plus 1/4, 1 square. And now what we can do, we can factor the 1/4 out. That will give us 1/4 square plus 1/2 square plus 3/4 square plus 1 square. And we can put that in the calculator, and that gives me exactly 0.46875. Okay, so now the area that we're looking for, notice the area of the shade region is going to be less than the area of the sum of all these areas of the rectangles. So if you add up all the areas of the rectangles, it's more than the actual area, because there's extra space here that we calculated or included in the area we just found that is outside the actual shaded region. So that's why we can say that the actual area is going to be less than this number. So what we did here, actually, we put what we call an upper bound on the area. This means the actual area will not be more than or equal to this area, to 0.46875. It's going to be less than that. We don't know how far less, but we know it's less than that. So notice what I did. I started from the right side and I drew the rectangle as I did earlier. But now I'm going to redraw the diagram again. I'm going to redraw the y equals x squared, and this was the 1. So now instead of starting at 1, I'm going to start at 0. So wait, let me write that down. 1/4, 1/2, 3/4. So at 0, remember how I did at 1. We went all the way until we hit the function and went to the left. Here we can go up because it's already there. And then so I have to go to the left, and now I go up. Then to the right, go up. To the right, go up. To the right, and go up. So remember, the area of the shaded I'm looking for is this. So what I'm going to do, I'm going to find the area of all these rectangles that you see. It's 3 of them because the other one is nothing, it's 0. So area A can be estimated with the sum of all these 4 rectangles. So if I want to start on the left side, the width again is 1/4. But wait, left side there's nothing in there, so it's just a 0 square plus 1/4. The height of the next rectangle is what? Is this distance from here to here. That's the height of the first rectangle. So it's 1/4 square plus 1/4. The height of the next one is 1/2 square. 1/4, 3/4 square. So then this equals to, you can factor 1/4 out. That gives us a 0 plus 1/16 plus 1/4 plus 9/16. So that gives me the area of all the rectangles, which equals to, I found it to be 0.21875. But notice the area of the rectangles is less than, like the total area of all of them, less than the shaded region because they fall below the curve. So we can say that the area, the actual area, is going to be more than 0.21875. So what we just did using this method, I was able to put a lower bound. This is called lower bound in the area. So in other words, now what we can do, area is bigger than this number that I just found and less than the number that I found earlier, which was 46,875. So this tells me where the area, the actual area, would fall in. So in mathematics, if we can prove something, if we can get estimated results, better than nothing. We say better than nothing. Okay, better than nothing. So the actual area is going to fall somewhere between 0.21875 and 0.46875. That's where the actual area is going to fall in. It's going to fall between these two numbers. Now, what happened if I take the same diagram, and then you might say, wait, why did you split into 4 intervals or sub-intervals? Well, we can split into 8, you can split into 6, 5, any number of x number of rectangles or subintervals you like. But what happens here is I'm going to redraw the diagram again. Okay, I'm going to redraw it here, show you something. So this goes this way. Say one is here. If we go up this way, we had 1, 2, 3, 1/4, 1/2, 3/4. That was the first one I drew. Now, what about if someone comes in and say, I'm going to split this into double the number of rectangles. So you start here, you're going to go up and this way, this way. Of course, wait, I should have included the black ones as well. This way, then 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 this way. So what I'm doing here is I drew another set of rectangles, but this is more. I have 8 rectangles now. Notice what happened when I increased the number of rectangles. Some of the space that was extra from earlier, like this highlighted space, it's not needed anymore. It's not needed, not needed. Do you see the highlighting? It's not needed. And guess what? The more I increase the number of rectangles, the less that space becomes, the smaller. So this means the more rectangles I use, the more I'm getting a better and more accurate result, closing or close to the actual result, close to the actual area of the region below the y equals x squared, below y equals x squared. So I hope that makes sense here to you. What happens is when I increase the number of rectangles, what happens if it's also, you take the one inside, it's the same thing. Like if you take the ones inside and you try to increase the number of rectangles, you will see that that space, the extra space here, this extra space, comparing to the area of the rectangles, this will get smaller and smaller. And then this will give us a more accurate area for the actual area A for the curve under the function. So if you like to see what happened for, I'm gonna call it n equals 8 rectangles. So if I split into 8 rectangles over the interval 0 to 1, then 8 rectangles or sub-intervals, you can say it either way, then we obtain this answer for the area. The area will be bounded between 0.27, 3435 and 0.39, 84375. Now look at this one and the previous result. This was between 0.21, 0.46 if you look at the first 2 digits only. 21 and 46. Here between 27 and 39. So these numbers, 27 and 39, are closer to each other than the previous part, which is 21, 46. So what does that mean? It means I was able to increase the lower bound and decrease the upper bound. So I'm getting an area or a bound on A that is really getting smaller and smaller. And the smaller the better. The smaller the better. So now, what about if we want to look at more rectangles? What happens? Like I looked at 4 subintervals and 8 subintervals. So what about if I increase that? So to do that, so I wrote that down here. If we have for 10 rectangles or 10 subintervals, the area, if you go through the work again, is going to be between, I'm going to just read the first 2 digits to the right of the decimal point, 0.28 and 0.38. So if you think about 38 minus 28, that's 10. The previous one, 39 minus 27, was 12. Do you see like had that number? What about if I have 20 rectangles? So that's 35 and 30. It's getting what? Smaller and smaller. 12, 10, 5. What about for 30 rectangles? It's 35 and 31. That's even 4. 35, 31. That's 4. And then for 50 rectangles, 34, 32, so that's 2, 12, 10, 5, 4, 2. And then for 1,000 rectangles, of course, there's a way like online to find this out. You don't have to do for 50 or 1,000. We usually go up to 10 at the most by hand. But then look how we got this. So start getting 0.3338 something and 0.332. Watch how close this is getting. So this is almost getting closer to 0. So the smaller or the closer these two numbers to each other, the better the value for the area. The better the value for the area. Now the question is, can we find the exact value for that area under the curve that we shaded earlier? The answer is yes, there is. But before we do this, let's look at some formulas that we learned back in pre-calculus, and we're going to use them here. What are the formulas? So we're going to recall. So here, this is an estimation. This is just an estimation based on these results, and I estimated the answer is going to be like this. Now the formulas, recall that 1 plus 2 plus 3 all the way up to n, it's n times n plus 1 over 2. And that's the sigma summation notation, the sum of I equals 1 to n. We also need to know, this is important to know, we need to know that the sum of the squares, 1 square plus 2 square plus 3 square all the way up to n square, is given by n times n plus 1 times 2n plus 1 all over 6. And the next one is 1 cubed plus 2 cubed plus 3 cubed all the way to n to the n cubed. That is really the square of the first one above. Is the square of the n times n plus 1 over 2. So that's the sum, 3 sums that we really need to know. We can apply them. We don't need to know 1 to the 4th, 2 to the 4th. Just up to the cubic one is really enough. Then we are going to see how we're going to apply such a thing in the same problem. So I'm going to go back and just pretend, I'm still working on the same problem. Now what we're going to do is, now let us divide the interval that we started with, 0 to 1, into n sub-intervals. Okay, n of them. I don't know how many, just n. Then the width of the rectangle is going to be 1 minus 0 divided by the number of rectangles or intervals or sub-intervals. It's 1 over n. So each rectangle or interval has a width of 1 over n. Okay, that's for each rectangle or each sub-interval. So usually what I like to do, I like to draw a number line here. So it started from 0 and it goes all the way up to 1. So if I add 1 over n, that would be 1 over n. Add another 1 over n, 2 over n. Another 1 over n, 3 over n. And this can go on and on. And that gives here n minus 1 over n, the last one. And the the one before the last one. And the last one is n over n. So this is like a map of the sub-intervals that we're going to be using here. And what we're going to do is, I'm going to let S sub n be the sum of all the areas of all the rectangles, of all the n rectangles. Okay, so what we do here, I'm going to find the sum Sn. Remember, to find Sn, we need the width times the height. So remember how this was, the graph went through this and went up all the way this way. So for the first one, the 0 doesn't do anything. So the first rectangle is going to hit at 1 over n. So the width is 1 over n, and the height or the length is 1 over n squared, plus the width the same width, and the height for the next one 2 over n squared, plus 1 over n times 3 over n squared. And this can go on and on all the way to the last one, which is 1 over n times n over n squared. So now we're going to rewrite this in a simpler form. simplify it. The first thing that helps me to simplify such expression is to factor 1 over n out. That will give me 1 over n squared plus, so 1 squared, 2 squared over n squared plus 3 squared over n squared. Notice I'm not simplifying the 2 squared, 3 squared because it's going to be easier for me to keep it this way. Now, the common denominator for all of this is n squared. So I can put n squared here. I get 1 squared plus 2 squared plus 3 squared all the way to n squared. And then, wait, what's n1 squared? That's the difficult part about it, is 1 squared, 2 squared, 3 squared. But we learned something about it today. We reviewed it from pre-calc, so we can go back to the formula and see what we got for that. We have 1 squared plus 2 squared plus 3 squared. Oh, it's here. It's there. It's n times n plus 1 times. So it's n times n plus 1 times 2n plus 1 all over 6. This is over 1. So that 6 is going to go in the denominator. So 1 over n times n plus 1 times 2n plus 1 all over 6n squared. And notice right away this cancels each other. So what do we get? Sn equals, on the numerator we get 2n squared if we multiply 3n plus 1 over 6n squared. Okay, so that's what we have so far. Now, this is the area under the curve of the n rectangles added together. Now, what I'm going to do here is to find the exact area under the curve. Remember from the previous example, as I increased the number of subintervals, n was started with 4, then 8, then 10, then 20, 30, 50, 1,000, remember? So as I increase the number of rectangles, in other words, as n gets bigger and bigger, we start getting a more and more accurate value for the area. So here what we do is, to find the area, the exact area, I'm going to take that sum and pass the limit as n goes to infinity. So this way you're making n to be really large, really large. So to apply to this one, limit as n goes to infinity, we have 2n squared plus 3n plus 1 over 6n squared. And what do we get in here? How do we find the limit of this? There's many ways to do this. This goes to infinity or infinity. You can use L'Hopital's if you like. N goes to infinity. L'Hopital on the top is 4n plus 3 over 12n. Oh, again infinity or infinity. We can use L'Hopital again. Limit as n goes to infinity by L'Hopital's rule is 4 over 12. So the answer is 4 over 12, which is 1/3. That's really the exact area under the curve, the area of the shaded. So this region here, you know, the 0 to 1. This is y equals x squared. This one here, the area under that, that's exactly 1/3. And guess what? If you divide 1 over 3 on the calculator, it's going to give us 0.33333 and forever. And notice when if you go back up here, our guess was this one. Notice how 0.333, very close, right? Very close. The one that we got as a bound for the first one, the first time we had the bound, it was this bound here in the box. It was between 0.21 and 0.46. So that was the first bound just for 4 subintervals. But if you have n of them and take n to infinity, that gives you exactly the area under the curve. Okay, so this is very important. Now, after we looked at the example, how we find exactly the area under the curve from 0 to 1 under y equals x squared graph, what about in general? What happens? How do we deal with this in general case? It doesn't have to be only specifically y equals x squared. That's what we're going to be seeing right now. So, the general case, we say in general, what do we have? If we have an interval a to b, we split it into n subintervals. N subintervals. Then the width of each interval each interval or subinterval is given by always b minus a over n, and we're gonna call this delta x. Delta x, that's the width of each subinterval or interval or rectangle. Okay, on the number line I'm gonna start with the first one. The first one I'm gonna call it that's a x0, then this is x1, x2, x3, and this can go on and on till the last one, xn. Before that would be xn minus 1, and xn is the same as b. So the width of each one of them, delta x, delta x, delta x, all the way to the last one, delta x. That's the width of each rectangle or each subinterval here. So the intervals we're working with is x0 to x1, the next one is x1 to x2, the next one x2 to x3, and this goes on and on to x sub n minus 1 comma x sub n. Remember, when we start finding the area of the first example, we start from the right side. Like, so what happened is we started with x sub n and then all the way down to x1. We kind of like did not use the 0, if you remember. So we can say then the right endpoints, if I want to find the right endpoints, they can be, if I want to find x1, how do I get x1 if I know a and b? Well, you take x0, add delta x. How do I find x2? Well, you just take x0 or a, if you like to put a, add another delta x. If you want to find x3, a plus, add another delta x. And this can go on and on, all the way to xn. xn is a plus. Notice how they match. 1, there's a 1. 2, there's a 2. 3, there's a 3. So I expect, since there's an n delta x. So we're going to be using this at some point. Now, when I started the first example, I start from the right side. That's called the right endpoint. You start from the right side. We're going to use r sub n, r for right, to equal what? We always, when we start finding or using the rectangles from the right side, we skip the first one on the left. So this means I take delta x times f of, I'm going to skip a, so I'm going to start x1 plus delta x, f of x2, plus it keeps going on and on until the last one, f sub xn, f of x sub n. And this can be rewritten as a sigma notation, f of x sub I delta x, where I changes from 1 to n. This is from the right side or right endpoint. The left endpoint is delta x. We start from the left, so x0 plus delta x, f of x1 plus all the way up to delta x, f of what? We do not count the last one here. So we counted the first on the left, we don't count the last one on the right. So this is f of x sub I minus 1 delta x. It depends, there's many ways to write this out. So I decided the subscript to be I minus 1. So I goes from 1 to n. So if you test it out, you will see that the line before it will work out nicely. Okay, so these two things motivate us to introduce a definition. The area A of a region lies below a continuous curve of a function call it f is given by, you either take the Rn, the right endpoints, as we did earlier, how we got in terms of n, and then pass the limit as n goes to infinity, or you can do the left endpoint and then pass the limit to infinity. Both of them will give us the same answer. Those things we have been working with are called Riemann sums. A German mathematician, well known for the creation of calculus, like really had so many contribution to calculus. And it's well known to people, to mathematicians, especially number theory. It has one of the things that made him the most popular is called the Riemann hypothesis. You can look it up and see it's still unsolved problem in mathematics. And it's ranked to be the greatest unsolved problem. Now this, what they give us, or what we did is we approached the area under the curve from the right side, from the left side, and we got kind of like bounds on it. Then we said if we increase the number of rectangles, we notice it's as we increase them, the more accurate the area becomes or gets. Now for this one, Rn and Ln, that's the left and right. It doesn't matter which one you choose, you will end up getting exactly the same answer. Was there other ways that Riemann approached to find the area under the curve? So if he starts from the right side, he noticed sometimes it gets the area bigger than what he wants, and maybe from the left it's less, or vice versa. He tried a different way. So what Riemann also did, he used what we call them the midpoint. Instead of just getting from the right side, started or left, he started in the middle. And how did he do that? Well, let's say we have any continuous function f, and we're going from A to B. And let's say I'm gonna split it into these rectangles. Let's say four subintervals. So the way he did it is he chose the midpoint of each subinterval, midpoint, and he projected this up, projected this up. And then from there he drew a horizontal line down to A, and the same horizontal line down to this. Same horizontal line through these, horizontal line through this, another horizontal line through these. So that's what he did. So now these points, we are going to call them x1, I'm going to call this star, x2, x3, x4. Okay, in general this can go all the way to xn star. So then the area, he said, is you find, take delta x times f of x1 star plus delta x times f of x2 star plus delta x times f of x3 star plus all the way to delta x times f of x sub n star. And in return, after this, because there's n of them, you take the limit as n goes to infinity. So if you want to rewrite it in a simpler way, this is the limit as n goes to infinity. We use the segment notation of f of xi star. Delta x stays the same, is not changing. Only the I changes from I equals 1 to n. So that gives us the area under the curve, the exact area under the curve, using the midpoint. And later on, and we will show you that, he found and proved that the midpoint gives always the best result than the right endpoint or the left. Because when we found the right end earlier, it gives us an estimation. We found the left end gives us an estimation. We don't know which one is the best, depending on the graph. Is the function increasing there, or is it increasing and decreasing? It depends. But always, regardless if it's increasing, decreasing, or both on that interval, the midpoint gives the better approximation than the other ones. So that's why Riemann was motivated to actually use this one. So for now, let's try to see how we can apply all the stuff we learned in this section to an example, another example. So let's start with saying let A be the area of the region located under the graph of y equals e to the negative x between x equals 0 and x equals 2. using right endpoints. Find an expression for A as a limit. As a limit. Let's start with this one first. So it says write endpoints. So R of n. So the first thing I do to make it easy for myself, it's 0 here. The first thing I'm gonna find is delta x, which is b minus a over n. B here, it goes from 0 to 2, so 2 minus 0 over n. So the width of the rectangle or the interval is 2 over n. So 0, add 2 over n, 2 over n, and this keeps going on and on until 2, which is 2n over n, like that. Okay, so these are the points that shows me what points am I going to use to find this. So it says right endpoint, so we start Rn. Since we're doing right endpoint, we skip on the first one. So if you remember, it was delta x times f of x1 plus delta x times f of x2. And this keeps going on and on, delta x until the last one, x sub n. For this specific one, delta x, we found it 2 over n, f of x1, this is x0. x1 is 2 over n. 2 over n, f of 4 over n. 2 over n, f of 4 over n. Sorry, n over 2n over n. Which you can write as 2 if you like. Then we can factor 2 over n out. So the function evaluated at 2 over n, it was e to the negative x. So that would be e to negative 2 over n plus e negative 4 over n plus plus e 2n over n. Like so. So what is happening here? Can I write this as a sigma notation? Well, we can. 2 over n, the sum. There's e in all of them. All of them, they have n in the denominator. Actually, there's a negative there. All of them, they have a negative sign. On the top, 2, 4, something, something like 2, 4, 6, 2n. So that's 2i, because any even number written as 2x or 2m or 2i. I goes from 1 to n, and you can test it. If you substitute 1 for I, you get the first one. 2, you get the next one. N, you get the last one. And then if I take the limit of this as n goes to infinity, which is the same by doing this on this side, so I can say then, this will give us the area. This is what the question is asking us to find. Okay, it didn't ask us to evaluate it, just find the expression. Now let's add another part to this. Estimate the area by using midpoints and using 4 subintervals. And same for 10 subintervals. And let's see what we get. So this is just an application to this specific example using the midpoint. So the midpoints, and they specified 4 subintervals only 4. Okay, only 4. So I'm gonna first draw the 0 to 2, and I'm gonna split it into 1, 2, 3, 4 subintervals. Delta x is 2 minus 0 over n. N here is 4, so that's 1/2. So this is 1/2, this is 1, 1.5, and 2. But remember, we're using midpoints. So we're gonna pick the midpoint here. Half of this is 0.25. Between these, 0.75. And then you notice every time from here to here they added 0.50. So add 0.50 to 1.25 and do it again, 1.75. So I got the points that I'm going to evaluate the function at, the green ones. So m sub 4 equals m sub 4, m for the midpoint and 4 for the number of sub-intervals, which is 4 here. So delta x times f of the first one, 0.25. Delta x times f of 0.75. Delta x times f of 1.25. Delta x times f of 1.75. So m sub 4 equals, we can factor the 1/2 out, which is delta x. F of 0.25 is e negative 0.25, e negative 0.75, e negative 1.25, e negative 1.75. And I put that in the calculator. Let's see what that gives us. If you put this in the calculator, it will give us 0.8557. So we can say A estimated equals 0.8557 using the midpoint. Now for 10 sub-intervals, it's the same thing. So for n equals 10, so delta x would be 2 minus 0 over 10. That's 1/5. And 1/5, if you like to convert to decimals, that's 0.2. So I'm going to put on the number line 0 starting with 0, and we need to split into 10 rectangles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the last one. That's 2 here. So here this is 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, and 2. Now the midpoints are 0.1, 0.3, 0.5, 0.7, 0.9, 1.1, 1.3, 1.5, 1.7, 1.9. These, the green ones, are the ones we're going to be using. Okay, those are the ones. So m sub 10 is going to be delta x, which is 1/5, times the function evaluated at 0.1 plus the function evaluated at 0.3 plus the function evaluated at 0.5 plus the function evaluated at 0.7. And this goes on and on until the function evaluated at 1.9. And let's see what that gives us. So this m sub 10 equals 1/5. This is e to the negative 0.1, e to the negative 0.3, e to the negative 0.5, all the way to e to the negative 1.9. So then m sub 10 equals, or estimated on the calculator, as 0.8632. So we can say A estimated is equal 0.8632. That's the estimated one. Now, what do you think? Like, just think about it. Would the actual area, the answer for the actual area under the curve, would be closer to this one, the 0.86, or the 0.85? Well, it should be closer to the later one, the 0.86, because as I said earlier, the more we increase the number of rectangles or sub-intervals, the more the accurate the area is going to be. The more the accurate the area is going to be. So that's what this section is about. We started called Riemann sums. What Riemann did, he started with evaluating the area under the curve from the right side. That was the first thing we looked at. And then he tried on the left side. And then after that, he tried to use midpoints, and he found that the midpoint is giving him more and more accurate one. And then he thought about, okay, if I take it to n, like n sub-intervals instead of just 4 or 10 or even 1,000, even when you work with n sub-intervals and you're okay with finding limits, it would be easier than finding the case when n is 100 or 10, even 10 rectangles. So that's why this gives us a strong value, let me call it, for the area under the curve. And then in the next section, we're going to see what he proved, found a shortcut to find the area. We don't have to keep doing this all the time. But that's how the whole area idea started in calculus.